I call it with a phi z. So basically here I is going to be E1 over Z, right, with the angle of delta minus Z minus E2 over Z with the angle of minus P, right? That's the power equation in this. Sorry, current equation in this circuit, right? Now we calculate P1. S1 is a P1 plus JQ1. What else I can say? If we use the RMS values, can I say it's going to be E1 I conjugate, right? If you use the RMS values. If it's the maximum values, I should put a half of this, right? But if you go with the RMS, it's going to be E1 I conjugate, right? Let's put it there. How much is the E1? It's going to be E1 with a delta times. How much is the I conjugate? Tell me. You guys tell me. Minus delta. I should change the sign of the angle, right? Right. So how much is the P1? And Q1, right? It's going to be imaginary and real part and imaginary part of the one, right? Let's put it here. How much is the imaginary part of this one? Let's time this one. It's going to be E1 squared over Z with how much the angle? Delta plus minus delta is going to be 0, it's going to be phi Z, right? Minus E1, E2 over Z with how much angle? Delta plus phi. Right? Did I get it correctly? Yes. P1 is going to be real part of this one. What is the real part of this one? It's going to be E1 squared over Z cosine phi Z minus E1 E2 over Z cosine, I'm going to write phi Z plus that, right? Our Q is going to be the imaginary part of that, right? It's going to be E1 squared over Z sine phi Z minus E1 E2 over Z sine phi Z plus that, right? Let me erase it. I want to use the bigger board, you know. Everybody can see that. Is it okay if I erase this part? How about S2? So basically, P2 and Q2 is going to be S2, right? S2 is going to be P2 plus JQ2, right? Which is the E2 I conjugate, right? E2 I conjugate. So let's put it there. So E2 I conjugate, E2 is E2 with the angle of 0 times I conjugate, right? So I should change the angle and times this one by E2, right? It's going to be E1, E2 over Z with how much angle? With phi Z minus delta minus something is wrong with it. E1 squared. No, sorry, this is correct. It's E2 times behind that. It's going to be e2 squared over z with minus pg, right? Not pg, because I have to conjugate that, right? Pg. Now, let's look at here, P2 and Q1. The real part of S2, see, I'm writing it for single phase, right? If you want it for three phase, just times it by 3, right? Whatever I'm putting here, you can times it by 3 to get it for 3. And this one is going to be imaginary part of S2. So, real part is going to be E1, E2 over Z cosine of PZ minus delta minus E2 power of 2 over Z cosine of PZ, right? And this one is going to be E1, E2 over Z sine of PZ minus delta minus E2 square over Z sine of PZ. Right. So I got the equation for P1, P2, and P1, Q1, and P2, Q2. Now I want to come with one assumption. Let's assume, or if R is very, very smaller than X, what's going to happen? So basically, Z is going to be equal to X with how much angle? Minus, let's put it. So Z is going to be equal to X, and how much is the PZ? 90, right? 90, correct? So let's simplify those equations with this assumption. Let's look at P1, P2. How much is the P1? PZ is 90 degree, right? This one is how much? 0, right? So PZ is 90 degree. Cosine of 90 plus delta, how much is it? Minus sign. Minus. And with the minus? Plus, right? So it's going to be E1, E2 over X, right? Sine delta, right? Right? How about the Q1? It's going to be, this one is going to be 1, right? Because PZ is 90 degree. It's going to be E1 squared over X, right? E1, E2 over X. And how much is this one? 90 plus delta. How much is sine 90 plus delta? Minus cosine. So we do cosine. Right? Sine in the first quadrant and the second quadrant is positive, right? So it's going to be cosine delta, right? So it's going to be E1. I'm going to factor in E1 over X. It's going to be E1 over X. From this one, we're going to have E1 is going to be left and minus E2 cosine delta. Right? So the equation becomes much simpler, with this one. Now let's hear what's going to happen to these two. P2 and Q2. Can you tell me how much is going to be P2 before looking at this equation? Sine delta.
Should be the same as P1, right?
Why?
Because R is so you start.
Because R is gone, there is no loss here, right? The only difference between these two is the power loss here, right? If we assume this one is 0, basically P1 and P2 should be equal, right? So if we put it here, I can say we're going to end up with this P1, P2 over X sine delta, right? Sine delta. How about Q2? Let's look at it. PZ is 90 degree, right? With sine of 90 minus delta? Cosine. I'm going to send you back to calculus. Two parts calculus one more time. 90 minus delta is going to be cosine delta, right? So it's going to be I'm going to factor in E2 and Z is equal to X, right? It's going to be E1 cosine delta minus E2. Right? I'm going to talk about this equation later. These are meaningful equation, physical meaning. I'll talk about it a little bit later.
No, I was asking why we calculating all
Because you want to calculate. When we have a synchronous machine, you want to see how much power we're sending out, how much power we're sending in. To answer his question, we're done for teaching today. You got this power equation, keep it in mind. So the difference between these two, Q1 and Q2, is going to be X I squared, right? That's the reactive power loss here, right? The between these two, Q is going to be X I squared. For equation, we are done. But let's answer this equation. You say, why are you calculating all these equations? So you look at here, for example, you don't have to write anything. We are going to repeat this one later. But this one could be a synchronous machine, right? Let's call this one EAF. How about we call this one EAF? Can I put it this way? EAF with delta, right? RX, RA, XS, and here's the VT. Right? Now look at here. That's very interesting. This delta, I told you, positive and negative. So current can go this way or can go this way, right? If delta is, for this case, I consider the current going this way, right? Going from this way. If delta is positive, what does it mean? Why? No, I'm not going to look at that one. Tell me with this equation, tell me what's the use of this equation.
Because real power P is positive.
And you see the power is going this way, right? Generator is the source, it's going to generate P, right? So basically it's sending power that way. If the delta is negative, what does it mean? Power is coming back this way, right? This machine is absorbing the active power, right? It's acting like a motor, right? Now let's talk about Q. That's very important. Let's look at here, Q2. Let's look at here. Is this one. This Q2, I'm going to talk about this one later. And your receiving power electronics too, also. Keep in mind that I'm going to repeat this equation in power electronics too because it's very important. When you have a synchronous, when you have an inverter, it can act like a synchronous generator. That's a new word, not 20 years ago, but now you can have that one with power electronics. Look at this Q2. Could be positive, it could be negative, right? If this one is more than this, it's positive. If this one is less than this, it's negative. What does it mean? If Q2 is positive, what does it mean? I'm sending, think about it. I'm sending reactive power this way, right? What does it mean? This is my green. My green. What does it mean? Green is like an inductor, right? You're supporting reactive power here, right? So you can do the power factor correction. Let's say your power factor, you remember from the power system, you had a power factor we want to correct it, right? You need something to generate reactive power, right? So here I can inject reactive power, right? I can improve power factor of my system. Or vice versa. If this one is negative, means the reactive power is coming this way. So basically, let's just stay here. If you look at here, reactive power is going this way. Means this one, this generator is acting like a capacitor, right? Because it's generating reactive power. But if Q2 is negative, means it's absorbing the reactive power. It's like an induction machine. It's like an inductor, right? Induction machine can only use Q. They cannot generate Q. But synchronous machine, they can go either way. If there's some synchronous machine, P is 0. They design it to have P 0. But they can change the Q as either positive or negative. They call it synchronous condenser machine. Those ones, they are very, very nice too for power factor correction. If you remember, with the power factor with the capacitor, it's like a steps. I can add something. For example, I can jump from 0.9 to 0.92 to 0.94 to 0.96, right? It's discrete. The jumps are discrete. But here is a delta. It's continuous. I can change my delta 0.1 degree, 0.2 degree, 0.3 degree, right? This one, it can change continuously. This is the advantage. Somebody tells me I need a 0.9352, power factor, right? I can do this with the capacitor. But what should I do? I should go with a very, very small capacitor to be able to do that. But here, I can set my angle to give you that power factor. If the synchronous machine is only used for power factor correction, they call it condenser. They call it condenser. if you hear about it. In power electronics too, I'll teach you how we can do the same functionality of the synchronous machine with a three-phase inverter. You don't have to have a synchronous machine as you're studying. You will have an inverter. We are done for today. You enter the break. The solution is here. If you want to see the solution, you can come look at this. Okay, there is a, if you look at top of your, first thing you do, quickly, count your grades. Make sure, I didn't make a mistake in counting. On the top there is, for example, AD plus 2. 2 is what you got for the writing, organized and clean,